thing we have to do is solve this structure. This does not give any angles or lengths, so we need those. Is there a solution to this in the? Yeah. Okay, so that's just a mistake in creating this problem. But let's say that, so I need to give those things. Let's say that this angle for both of them is 80 degrees. And let's say that the lengths are 1 meter. Okay. So those have to be given. And let's number these. I'll call this one 1 and this one 2. So free body diagram of body 1. Looks like this. It's a pin joint at the bottom. I'll call that RA. And then they're connected at the middle. So that's F12. And then up at the top, this member is only connected to the cable once. And so you have a force like this. And there's no masses. Anybody have any questions about that? And then I'll use this as my about point. So RA has 0 row vector. Force vector is RAX, RAY. Cross product is 0. Then F12. That is it's a length of 0.5. The angle is 80 degrees. So 0.5 times cosine and sine of 80. Is 0.087 and 0.492. Force is F12X, F12Y. Cross product is, I wrote this wrong. This is 0.087. So we got 0.087 F12Y minus 0.492 F12X.
Wait, that's just cosine sine of
80 times 1/2 because it's a length of 1/2 a meter. And then T is a length of 1 times cosine and sine of 80. So that is 0.174, 0.985. The force is negative T0. So the cross product is positive 0.985 T. And so the equations, the first one says RAX plus F12X minus T is equal to 0. We know that cable force is 300. I put it in as T. Let's see.
have to change the bottom of your graph.
Yeah, so let's just, I don't know. I could, might as well put this in here. We could also just carry it through as t and our equation will solve for t, but so that is positive 295.5. And then the second equation says RAY plus F12Y is equal to 0. And the third equation says negative 0.492 F12X plus 0.087 F12Y is equal to negative 295.5. We have 4 variables, 3 equations, so we just have to keep going. So free body diagram of body 2. We have a force RB down here, a force negative F12 here, and then the cable force acts twice. And in both cases, it's parallel to the cable away from the body. So we have 300 and then another 300. Any questions about that free body diagram?
Can't you solve for the variables before you even do the second free body diagram?
No, I don't think so because we have 4. Yeah. Yeah, because so what I'm going to isolate up here is like all of this, a little bit of that cable, a little bit of that cable. Let me in there. Okay, so what you have is 2 cable forces coming out of those little stumps of cable. Those are the external loads. And so you have something parallel to the top cable away from the body and something parallel to the bottom part of that cable away from the body. So rho, force, moment. And I'll put my about point here. So first I'll do RB. The rho vector is 0. The force is RBX, RBY. Cross product is 0. Then negative F12. The rho vector is negative 0.087, 0.492. That's 1/2 times cosine and sine of 100 degrees. Force vector is negative F12X, negative F12Y. Cross product is positive 0.087 F12Y plus 0.492 F12X. And then I'm going to lump these 2 things together. If you wanted to be real careful, we've done ones like this before and seen kind of how it works out. But you could do one as like with a plus R, one as a minus R of the pulley. we're going to assume that that radius is just 0. Or if it wasn't 0, it turns out they cancel out in a way that makes it act just the same way. So I'm going to just call this a 600 Newton force that acts at negative 0.174, positive 0.985, and the force is 600, 0. And so that is negative 591. Bless you. So equation 4 says RBX minus F12X is equal to negative 600. Equation 5, RBY minus F12Y is equal to 0. And equation 6 says 0.492 F12X plus 0.087 F12Y is equal to 591. Okay, so we have 6 equations for 6 variables. So 6 rows, 7 columns. These are equations 1, 2, 3, 4, 5, 6. And I'll do it as RAX, RAY, F12X, F12Y, RBX, RBY. Was that the sound of someone having a great idea?
Sure, supercell.
Let's see. So equation 1, RAX and F12X are 1. And the constant is 300. Then we have RAY and F12Y. Then negative 0.492. Let me just check. So negative 0.492. Right. Positive 0.087. And the constant is negative 295.5. Then equation 4, RBX is 1. F12X is negative 1. Constant is negative 600. RBY is 1 for the next equation. F12Y is negative 1. Constant is 0. And then for the last one, F12X is 0.492. F12Y is 0.087. Constant is 591. So what I got is, for RA, negative 600, actually 601.0. And then negative 1690. Negative 1698.3. Is that believable.
That seems way too high.
Yeah, it does seem odd that the vertical one would be that high.
Especially when there's no lake.
Right. Did anyone else punch these in?
Yeah, that's all I got.
Okay. Well, sometimes you get confusing things, but
I mean, I guess it makes sense that as they're closing, the horizontal component of both of those base joints is probably going to cancel out, and then all of that force is going to go straight down into the joint.
yeah, maybe. Okay. Well, so RA, is that F12? Is positive 900.9, positive 1698.3, and then RB is 300.9, 1698.3. Okay, so now we're going to represent these as external loads on free body diagrams because we're trying to get to calculating the internal loads. So for body 1, we have a force vector down here of negative 601, negative 1698.3. We have a force at the middle of 900.9, 1698.3. And then up at the top, we just have the 300. And then for body 2, we have RB. That's 300.9, 1698.3. We have negative F12 at the middle. So that's negative 900.9, negative 1698.3. And then this is 600. Okay. So now, in order to calculate the internal loads, we're used to these beams lying flat. Right now we have them up at these angles. But what we really need to do to lie them flat, it's not really about how they're positioned on the page. What it really is about is how they're positioned relative to the coordinate system. So if we're going to do this one first, what we really want is we want to express all of these forces in terms of a coordinate system where the x-axis goes along the length of the beam and the y-axis is perpendicular like that. Okay, so can anyone think of a way to calculate these? So we have these 3 force vectors. How can we calculate those in this red coordinate system? Yes? You can use a rotation matrix. That's the easiest way. You also can do it as projections. So if you ever, you don't want to go back and read about rotation matrices or whatever, you can always just say, okay, we want to take this vector, this negative 601, negative 1698, and we want the projection of that first in the direction of the positive x-axis, and then second in the direction of the positive y-axis, and that'll give us our two components. Okay, so what you could do here is you could go, so negative 601.0, negative 1698.3, dotted with a vector in the direction of the positive x-axis. That's how we get that projection. So using our old coordinates, this would be 0.174, 0.985. That's a unit vector in the direction of the positive x-axis.
Wait, where's that unit vector coming from?
Well, that vector is at an 80-degree angle compared to our, so I'm just using cosine and sine to get a vector that's along that. And then the next one would be, so that would be use cosine and sine of 80 degrees. This y-axis would be cosine and sine of 80 plus 90, so 170. And you get negative 1777.4. Okay. So on, and you'd have to keep doing these for x and y components of all of these. So you'd have to do this twice for this one, twice for this one, twice for this one, and that would give you your components. So we do x and y for each force vector. Or we could use a rotation matrix, which is so much faster. Okay, so in this case, we start with our original coordinate system. And we think about what kind of rotation we would need to go to our new coordinate system. That rotation is 80 degrees. And is that, to go from the left to the right, is that a clockwise or a counterclockwise rotation? It's counterclockwise, so this is positive. So now we just plug these values into the definition of the rotation matrix. So cosine of 80, sine of 80. No, the negative is down here.
Wikipedia says the negative is on the other one.
Let me think. So we're trying to go, let me not think, let me just look.
It might be different if we're rotating counterclockwise or clockwise.
Oh, you Googled it. Okay. So yes, that is something, there's something tricky about rotation matrices, that something that can trip you up very easily that I didn't mention. There are two ways to think about a rotation matrix. There's one that rotates a vector and keeps the same coordinate system, and there's one that rotates the coordinate system and keeps the same vector. We're using the one that keeps the same vector and rotates the coordinate system, and those two are opposite of each other. It's a pain.
Wait, would you do these on the test, do you think?
No. But you should understand the thing about projections. It's a really useful thing to understand. So let me just look at this. Okay, right. So to rotate the coordinate system and keep the vector the same, it's cosine, sine, negative sine, cosine. To rotate a vector and keep the coordinate system the same, those negatives switch. It would really be, and so I strongly recommend that you choose one of these two types of rotation matrices and do everything thinking about it that way. This is the way I always do it. Think about rotating the coordinate system. Okay. What? Yeah, that's right. That's right. Cosine of 80. Okay, so if you punch this in, you get 0.174, 0.985, negative 0.985, 0.174. But now we just have to multiply that. Yes?
You said for this, when we do rotation matrix like this, it's always going to be like this formula where that bottom left one is negative, right? Or does it change?
It's always going to be this formula: positive, positive, negative, positive. Yep. And for the people taking deform with me in the spring, we're going to use these all the time. But I mean, I'll give you more background on it too and stuff. Okay, so now that we have this, now we're just going to multiply it by these force vectors one by one. So so this matrix times negative 601, negative 1698.3. is negative 1776. That's why I use these numbers to get a patriotic answer. And then positive 297.0.
1776.9, the September of 1776.
That's true, yeah. That was the most patriotic month. Okay, and then do it for the next one. So Q, same Q times 900.9, 1698.3, and this one spits out 1828.9, negative 592.3. And then do it for the last one. Q times, that vector was negative 300, And so the answer is negative 52.1, positive 295.4. So now if I redraw this free body diagram, what we have is we have our force vectors representing a coordinate system like that. So this one is negative 1776.9, 297.0. This one is 1828.9, negative 592. And this one is negative 52.1, 295.4. In other words, now you can just draw it like this. I mean, the actual orientation of it really doesn't have anything to do with anything. All that matters is the relationship between our coordinate system and our forces. So now we can write this like over here we have negative 1776.9, 297.0. At the middle, we have 1828.9, negative 592.3. And at the end, we have negative 52.1, 295.4. Okay, so now that's just an easy internal loads problem. How many cuts? Yeah.
So for doing the Q and the multiplier, we're doing the first one was Q with RA, then F12.
Yep.
The last one's RB.
No, the last one was that 300 pointing to the left.
And then the bottom was 1698.3. Then in your calculation below it, well, you did 300. Is that?
Yeah, I'm just going. So there are three force vectors, and we're just doing them one by one. So the first one, we multiplied the matrix times RA.
Right.
The second one, we multiplied by F12. And the third one, we multiplied by negative 300, 0. Just that T vector.
Okay.
Okay, so how many cuts do we need here? 2. Yep. And so, I mean, this is an easy problem. So cut 1 is for x's between 0 and 0.5. We have the force vector over here of negative 1776.9, 297.0. We haven't gotten to the middle force yet, so the only thing we have left are T, V, and M. So Newton's second law says negative 1776.9, 297.0 plus T negative V is equal to zeros. So T is equal to 1776.9. V is equal to positive 297.0. And then the moment equation, all we have is plus M minus Vx is equal to 0. So M is equal to Vx, which is 297x. And these are valid on the interval 0 to 0.5. And now we go to cut 2. Our x's go from 0.5 to 1. So over here we have negative 1776.9, positive 297.0. Now we also have to include that force at the midpoint, which is 1828.1. Negative 592.3. And then T, V, and M. So Newton's second law says negative 1776.9, 297.0 plus 1828.1 negative 592.3 plus T negative V is equal to zeros. So the internal tension is 51.2. The internal shear force is negative 295.3. And then the bending moment, so we have, okay, so for this force at the midpoint, notice that the horizontal component doesn't produce any moment. The horizontal component just goes right through the about point. So all we have is a downward force of 592.3 and a moment arm of 0.5. So we have 0.5 times 592.3. That would make it rotate clockwise, so this is negative. Plus m minus Vx is equal to 0. So m is equal to,
Are these in all in Newtons then?
these are all in, well, the bending moment is in Newton meters.
Oh, yeah.
So m is equal to negative 295.3 plus 296.15. And this one should be multiplied by x. What do you do if you, so we didn't include weight in this. What if we did include weight in this and you had to include that in your internal loads? Well, remember weight is a distributed load. So you'd have to go through this whole procedure with your distributed loads too, and you'd come up with horizontal and vertical components of distributed loads. If you're interested in that and you want to read about it, it's in the textbook thing, my textbook, that's that's on D2L, but I'm not going to give you any problems on that this semester.
Professor,
Yep.
so like if we have a problem with internal loads, it shouldn't be like this
What?
on the
Like, is
exam.
this gonna be on the?
No, I
Like,
won't make you do
internal
this stuff
loads
on the
will be,
exam.
but not something this complicated where we do
Right.
the homework problem
That's
and
right.
just spend the
I
whole
won't
time.
make you do, in 50 minutes, I don't have time to make you do a structure and do the internal loads anyways, but I won't put anything on the exam where you solve a structure and then make it internal loads, but you should take a good hard look at this stuff, try to do those problems, I think it's an important part of understanding how these pieces fit together. Yeah.
How long is our final?
Oh, the final is 2 hours. So I guess that's a good point. Maybe I can give you this.
Oh,
No. Yeah, you have 3 hours, but I do mine is a little shorter in just 2 hours. Was there another question over here? Any questions?
And then you have to do this whole thing over for the other.
For the other one, yep. We did half of it here. And then you could
Was
plot
there-
these out. These are piecewise functions. This is valid only for x between 0.5 and 1.
Professor,
Mhm.
so the other joint, it has like if we shift it, it just has the connection is on the end, right? For the 300 newtons. plus.
Oh, yeah, it's on the end. That's why it didn't come up in the internal loads.
Okay.
I mean, it comes up in a way because we've already solved for all the external loads, but you never explicitly use that 300 Newton force for the internal loads. Remember, whatever happens on the far right end of any beam doesn't explicitly show up in the internal loads.
So if we tried to do 2, would you like recommend that we sort of redo it again so where it's 100?
Mm-hmm. So yeah, you have 2 options. You could do it so it's
Or-
100 and use this coordinate system. Or you could do it as negative 100 or positive 260, and then your x-axis is like that and your y-axis is like that. Either one is fine. The functions look a little different, but they give you the same information. Any other questions? Okay, that's all.